So I want to take a look at the use of non-dimensional coefficients. Why do we use non-dimensional coefficients? So let me just start by defining a particular problem that we'll take a look at. So we've got an airplane, and I'm going to have the flow velocity be v infinity. You can see the airplane's at an angle of attack, so let me write that in as well. Some other quantities that may be useful in determining, say, the lift and drag on an airplane would be, I might expect the density in the free stream to be important. Might think the speed of sound in the free stream could be an important parameter. And say the viscosity also might be important. So mu is the viscosity coefficient, and we'll get into this more later in the semester. We'll talk about it more later. But the viscosity coefficient controls how much frictional forces are important in the flow field. The things we're interested in might be the lift and drag, for example. So I've drawn those in here. Could be other quantities too, but we'll look at the lift in particular. And so we're going to think about how does the lift depend on all of these parameters and the geometry as well. But what I'm going to do with the geometry is I'm going to think of this airplane and I'm going to keep that fixed, but I might allow the airplane to increase or decrease in size, but it would have its same shape. So I'm going to use the planform area, or not the planform, the reference area, SREF, as a measure of what's the size of the airplane that we're interested in. But we're going to keep the shape fixed here. So the lift then would be a function of 6 different parameters. The reference area, which sets the magnitude of the overall size of the airplane, the free stream velocity, the angle of attack, the density in the free stream, speed of sound in the free stream, and the viscosity in the free stream. So I've got the geometry with these 6 parameters. I think will tell me what the lift would be, would define the lift. Now, of interest is how does that lift in the full-scale model relate to the lift in, say, a wind tunnel test we might do. So in the wind tunnel test, we'll have usually a smaller airplane, and the wind tunnel will have its own set of parameters. So we'll define the lift in the wind tunnel to be a function of the same 6 parameters, but those parameters may have different values because it's in the wind tunnel. And in particular, we're thinking that SREF is likely to be different between the full scale and the tunnel. But these other parameters may as well. Okay. Now, of course, as you'd expect, the angle of attack is not going to be different if I'm going to want to be looking at the same flow. So alpha in the wind tunnel and alpha in the full scale are going to be the same here. But just to be consistent, I've labeled them alpha without the subscript and alpha t for the wind tunnel. But we know they're going to have to be equal if we want the flows to be related to each other in some way. Okay, so overall question though is how does the lift in the tunnel or the scaled test relate to the lift of the full scale version? And to get a little bit of an understanding of that, we're going to use this theorem called the Buckingham Pi theorem. Okay, the Buckingham Pi theorem relates the number of dimensional units in the problem to the number of parameters in the problem. And so what do I mean by dimensional units? Well, that's just the units of measure that are needed to describe this problem. So for us, if you look at all of the different parameters I have here, whether it's speed of sound, density, viscosity, lift and drag, they are all in units of mass, length, and time. Some combination of mass, length, and time. So for us, our dimensional units are mass, length, and time. That means that ND is 3. Okay, and then the number of parameters that I have that are the input parameters, if you will, that will control the quantities I want to determine. I'm going to have 6 of those, right? The 6 that I've just listed here. So NP is the number of parameters in the problem. And for us, we're going to have these 6. So NP is equal to 6. Okay, and what Buckingham Pi says is that any non-dimensional quantity are determined by just NP minus ND non-dimensional parameters. So I have a dimensional form of the problem up here, which is the lift is a function of 6 dimensional parameters. But when I non-dimensionalize the problem and look at a non-dimensional version of the lift, which we know will be the lift coefficient, it's going to say that the lift coefficient depends on NP minus ND non-dimensional parameters. So that's going to be 3 for us, right? NP minus ND is 3. 6 minus 3 is 3. So instead of having a 6-parameter problem, I'm now going to have a 3-parameter problem. And the 3 parameters are going to be non-dimensional. Okay, so for us, NP minus ND is 3. What that means is some non-dimensional version of the lift is going to be a function of 3 non-dimensional input parameters. So now I've simplified the problem a bit. I've gone from 6 input parameters to 3. The other thing that's happened is they're all non-dimensional now, so the scale of the problem doesn't directly come in. There are many ways I can do this non-dimensionalization. There's not a unique way to do it, but what's done in aerodynamics usually is we use the lift coefficient as the non-dimensional lift, and then the 3 parameters that we tend to work with in non-dimensional forms are the angle of attack, which is already non-dimensional. I mentioned that, the Mach number, and the Reynolds number. The Mach number, you could be familiar with that. That's the ratio of the velocity of the air, or the velocity of the aircraft, and the speed of sound in the air. So that's the Mach number. And the Reynolds number is the other parameter that is typically used. And you can see here the definition of the Reynolds number, okay, where it's the density, velocity, and some reference length, I'll tell you about that in a second, divided by the viscosity. So the Reynolds number, because it has the viscosity, relates how much frictional forces are going to play a role in this. And since Reynolds number is a 1 over the viscosity, the larger the viscosity, the smaller the Reynolds number, and vice versa. If I have very small viscosity, and that means what we would think very small viscous effects, then the Reynolds number is going to be very high. And this reference length scale is for me to pick. What's usually done is you pick it as something like the average chord length of the wing. So if I draw an airplane here and I'm looking down on it, so when I look down on an airplane, that's my planform view. I'll take a cut of the wing to produce an airfoil section. That length scale of that airfoil is called the chord, so that's the local chord, and we call it the local chord because the chord varies depending on where I am along the wing here. So if I'm at the wingtip, it's a smaller chord. If I get to the root, the chord is longer, and typically LREF is set as some kind of average chord length. Okay. The thing to note is that I haven't actually defined a new length scale in the parameter. If I just say I want the average chord, given the geometry, if I haven't changed the basic shape, and given SREF, the planform area of that geometry, then I could find LREF. If I introduced a new parameter into the problem, then I would have another input parameter I'd have to take into account here. I'm not doing that. I'm just making a particular function of the geometry and SREF. Okay, so what does this mean about wind tunnel testing or scaled testing? Well, it says that what I'm going to be interested in doing is producing the same lift coefficient between the tunnel and the full scale. And the way I'm going to do that is I need to make sure that my non-dimensional input parameters match. So if the angle of attack, Mach number, and Reynolds number in the tunnel match the angle of attack, Mach number, and Reynolds number in the full scale, then the lift coefficients will be the same between the tunnel and the full scale. Of course, the lift won't be the same in most cases, but the lift coefficient will, and that's what matters here. So I can do wind tunnel testing where if I match the input parameters non-dimensionally, then I will have the same non-dimensional coefficients, and I can use then the non-dimensional results from the tunnel to tell me what the non-dimensional results for the full scale are, and therefore what the lift in the full scale would be. Okay, this idea is more general than that. This is true for any non-dimensional quantity. and the idea here is, the more general idea is called flow similarity. And so the idea would be, if I have the same non-dimensional input parameters between two flows, then the flows will be similar. Any quantity appropriately non-dimensionalized will be related to the quantity in the two flows, will be equal to the quantity in the other flow. So let's say I've got the density in one flow. So the subscript 1 says it's some flow, which is going to be similar to a flow 2. I want to know how that density depends on x. Okay, and I want to know how that relates to the density in flow 2, how its dependence on x is related between flow 1 and flow 2. Flow 1 and flow 2 are similar, so they have the same alpha Mach number and Reynolds number and same geometry. How do I relate them? Well, I'm going to non-dimensionalize them, and you'll note here what I've done is I've non-dimensionalized both the density, so rho 1 is going to become rho 1 over the free stream value of rho, but I've also non-dimensionalized the x value, right? So x is scaled by the reference length for geometry 1, flow 1. And if I do the same thing for flow 2, then the non-dimensionalized density in flow 2 is equal to the non-dimensionalized density in flow 1. And I can do the same thing for the velocity. So suppose I took the velocity between the two flows, non-dimensionalize each velocity by its own free stream velocity, then the velocity's dependence on x, non-dimensionalized by the chord length again, or the LREF, these are going to be equal to each other. So again, any quantity in the flow field, when it's non-dimensionalized in the right way, will be equal to the quantity in any other flow field which is similar to it, so as long as the input parameters non-dimensionally are the same.